Okay, good evening, good afternoon, good night, good morning, depending on when you're watching this. Um, this is going to be probably part one of three from lecture set 10. Lecture set 10 has, it's about three different hypothesis tests, no confidence intervals. The three tests are the chi-square goodness of fit, the chi-square independence, and the ANOVA F test, which is called the one-way ANOVA on the table of contents. So my plan is to make a video for each test and then post those afterwards. So we'll go in order. So the first test we're going to cover is the goodness of fit test. Now, before we do that, I just need to talk a little bit about the chi-square distribution. So we have learned about the standard normal distribution and the student t distribution. We have learned about those two continuous probability distributions. We did talk about other discrete distributions earlier in the course. The chi-square is a continuous distribution like the standard normal and like the student t. So it emits a density curve. And effectively, what we have to be able to do is find area underneath this density curve or find critical values if we are given an area underneath this density curve. That is basically we are using this the same way we use the student t curve or the standard normal curve within the context of a hypothesis test. Now, the chi-square is different from the student t and the standard normal in that it does not center at zero. It actually starts at zero and only moves in the positive direction. So it's a density curve that exists for only positive real numbers. So chi-square is a literal term, like a chi value squared. So it's always positive because anything squared is always positive. You can see from this slide that the chi-square distribution is a right skewed density curve, unlike the standard normal and student t, which were symmetric density curves. And you can see that there's a degree of freedom parameter associated with this curve, and that degree of freedom parameter effectively controls the shape. So you'll notice that as the degree of freedom is increasing, the skewness is moderating, or it's sort of fading out a little bit. Okay, so once again, we have to be able to find critical values and p-values using this curve. Now, this curve, just like the student t curve, for example, emits a table, or we have a table that is associated with it. Now, that table has two pages. This is page one, okay, and then this is page two. Now, the way that we read this table is exactly like we read a student t table. The only difference is that both tables have the same degrees of freedom on them. And you'll notice that the tail areas at the top, so those values shown here, those are actually very large on the first page, which is somewhat unusual given what we have seen with the student t table. But then as we scroll across any of these lines, so we're reading the tables horizontally as if they were beside each other. As we scroll across these lines, we come to page two, and now our tail areas shown here start to look more familiar. And most often we're going to be on the second page of the chi-square when we're looking for critical or p-values. But having that first page just allows us to do some fancier bounds. And I'll show you an example of how to use this table within the context of the chi-square tests in a little bit. Okay, so once again, we're going to talk about two chi-square based tests, but in this video, we will probably only talk about the first one, and then I'll post a second video for the second chi-square test. But both those tests use the chi-square table, and we're using those tables in the same way that we used our student t table, for example. Okay, so the first chi-square test is called a goodness of fit test. This test has a very specific application. First of all, it's applied to counts for qualitative outcomes. So, for example, you can see I have on the slide here, suppose that you're playing a game where you roll a single die, so one six-sided die. Now, you want to make sure that the die that you're rolling is a fair die, which means that every number comes up the same probability or the same number of times. Like, so what I mean is there's a 1 out of 6 chance of getting each number on the die. That's what fair would mean in the context of this example. So you roll that die some number of times, say 500 times, and you count how many ones you get, how many twos you get, how many threes you get, fours, fives, and sixes. Now you can use those counts to assess if each number is rolling the same amount of times as you would expect them to do. And that's what the chi-square goodness of fit test is for, is effectively to determine if the portion that you expect to be true for each outcome that you are dealing with is actually being met. So this test has a very specific purpose. And a lot of the time when I teach this, I try to sort of explain like this test is for one qualitative outcome where you have a frequency distribution for that one qualitative outcome. Whereas the independence test, which we will talk about after this, is for two qualitative outcomes, and then you would have a contingency table for the counts from those two outcomes. So one of the ways that you can pick out this test is basically by saying, do I have numeric values or do I have a qualitative variable with a frequency distribution? And if I have that, the goodness of fit test is really the only one that will apply. Okay, so like every hypothesis test that we've talked about in the course, we start with an assumption check, and then we have 6 steps. Now, the assumption check for the chi-square goodness of fit test has our usual, a representative or simple random sample was collected. You can see that's the third assumption. And then we also have these 2 assumptions that are based off of what are called expected frequencies. And these expected frequencies are values that we need to compute. Okay? So I typically will refer to the expected frequencies as capital E, and these are something that we will actually calculate ourselves within the chi-square test. So the chi-square test actually starts with calculation of the expected values, capital E, the assumption check, and then we move into our hypothesis test, which again has the same 6 steps that we've looked at for all of our hypothesis tests. Now, for the hypotheses, we kind of have a stock, null, and alternative that don't really change for any of the given problems. So one of the things that you can do when you're learning this test for the first time is sort of just repeat these hypotheses, and they are general statements that are always what this test covers. In the examples that I show, I will tailor these a little bit to what we're actually talking about, but the general statement is the variable follows the specified distribution. So for example, the outcomes on the die have a probability of occurring of 1/6, or the variable does not follow that distribution, which just means that one number on the die can deviate from or not have a probability of 1/6 of occurring, or multiple numbers on the die cannot have the probability of occurring. So the variable not having the specified distribution has a lot of possibilities. On the second step, significance level, on the third step, we compute our test statistic. The test statistic here is the sum of what we call the observed, capital O, minus the expected, capital E squared, divided by expected. I'll show you an example of how this works in a bit, but this is an addition of that fraction however many times, or for however many outcomes we have in the experiment. Step 4, find the critical or p-value. Note that because the chi-square is a right-skewed distribution, this isn't exactly why, but because the chi-square is a right-skewed distribution, we actually only test in one direction in this setting. So we don't have to worry about this concept of being one-sided or two-sided anymore. We can simply just find the critical, given whatever the significance is, or find our p-value, which is always going to be the upper tail area. On step 5, we use that information to determine if we should reject or not reject in the normal way. And then on step 6, we interpret. Okay, so the test statistic, which is shown here, again, is a summation of 2 values. So we have the observed values, which are this is the data. So these are the counts that will actually be given to us in whatever the illustration is that we are working with. minus the expected value, which again, we calculate. So the very first thing we do once we've identified it's a chi-square test is we calculate these expected values. We square that difference, and then we divide by the expected value. And then we add that together for however many outcomes we have. The degree of freedom associated with this test statistic is equal to C minus 1, where C is the number of observed values or the number of outcomes. So for example, in the die rolling illustration, there are 6 possible outcomes on a die, so little c would be 6 in that case. To compute the expected values, we take our sample size and we multiply it by the theoretical probability of observing that outcome. And this will make more sense via illustration. But in the case of the die rolling example, let's say that I observed 90 ones when I rolled the die 500 times. The expected number of outcomes would be 500 times 1 over 6. And then we'd be taking the difference between 90 and 500 divided by 6. Okay, so let's look at an example. In this illustration, again, what we have here are counts, or sorry, the probability of getting a particular color of M&M in a standard bag of M&Ms. So this first table is a probability distribution, right? This is it's a probability distribution or a percentage distribution. It's one qualitative outcome. So the outcomes of interest are colors, qualitative variable. We have a probability associated with each qualitative variable. So the chi-square goodness of fit test is the test that would apply to this type of data, qualitative outcome. So we have 6 different outcomes, colors that we could observe in a bag of M&Ms. So according to the company that makes M&Ms, 30% of the M&Ms should be brown, 20% yellow, 20% red, 10% orange, 10% green, 10% blue. Now the question is this actually true? So if I buy a bag of M&Ms, will I actually observe that 30% of that bag are brown, 20% yellow, 20% red, 10% orange, 10% green, 10% blue, right? So this is the question. Does an actual bag adhere to this stated probability distribution? So we purchase a bunch of bags of M&Ms, we dump them all out on a table, and then we sort them by color. So in total, we have 509 M&Ms, right? So this is the total number of M&Ms in the sample. 152 of those are brown, 114 are yellow, 106 are red, 51 are orange, 43 green, 43 blue. So these are the observed counts. Okay, so these are the capital O that I had referenced on the previous slide. Okay, so with this type of testing, what we're always going to be given effectively are this type of frequency distribution. So here's an outcome for some qualitative value, in this case colors. This is what we actually counted, and then we're going to be told that the true distribution of whatever we're studying, in this case colors, is going to have these probabilities of being associated. Each outcome in that distribution will have a given probability of being observed. So then the question is it true, based off of this sample, that 30% of the bag are brown, 20% yellow, 20% red, 10% green, 10% orange, 10% blue? That's what we're trying to ask, or trying to answer. Is it true that this color distribution is as stated by the company? Okay, so to do this, we're going to use a goodness of fit test, because again, the chi-square goodness of fit test is the only test that applies to one qualitative variable. So first, we calculate our expected values. Right? So the expected value calculations are summarized in the table shown below. Okay, so you can see what's going on here, but just to highlight this, right? So this will be number 1. We have the expected value of brown M&Ms is equal to the sample size minus times the probability of observing a brown M&M, which is 509 times 0.3, which is the 152.7. Okay, so this table is just, again, summarizing that formula provided on the previous slide. Similarly, here, like for yellow, and red, it would be the same calculation. We have n times the probability of yellow. So that's going to be 509 multiplied by 0.2, which is 101.8. Okay, and then just for the sake of completion, this would work for orange, green, or blue. Okay, so we have n times the probability of green, which is 509 times 0.1, which is 50.9. Okay, so these values here are the expected values that we have to calculate. So the start of the chi-square is always going to be the calculation of these expected values. In this case, we have 6 of these values we have to calculate because there are 6 outcomes in our distribution. Once we have computed the expected values, the next thing we have to do are check the assumptions. Now again, we have 3 assumptions. The first assumption is that no expected value is less than 1. Okay, well, our lowest expected value is 50.9. 50.9 is bigger than 1, so therefore we have no expected values less than 1. So here, every E is greater than 1. Okay, the second one is a bit trickier to conceptualize, but the second one states that no more than 20% of the expected values are less than 5. Okay, so we have little c is equal to 6 different outcomes. So 20% of 6 is 1.2. So we are saying that no more than 1.2 of the expected values are less than 5. So in the context of this problem, it means that if we had 2 expected values that were less than 5, this assumption would not be met. But if we only have 1 expected value less than 5, this assumption would be met. Now, in this case, our lowest expected value is once again 50.9. 50.9 is bigger than 5, so we have 0 expected values less than 5. So we are once again okay here. So every expected value is greater than 5. Okay. So that calculation I did, the 0.2 times the number of outcomes, that would be the way to start off the second assumption. And again, that's a cutoff. So if I have more than that cutoff, if more of the expected values than whatever that number is are less than 5, that assumption is not met. In this case, 1.2 is the cutoff. So if we had 2 expected values less than 5, then this assumption would not be met. But in this case, none of them are, so it's fine. Okay, so the test itself, step 1. So again, the null hypothesis is just that whatever the distribution is that is stated or assumed to be true, that distribution actually will hold. And the alternative is simply that that distribution is not going to hold. So in this case, the distribution that we are testing against is the probability distribution given at the start of the problem. So the question that we are asking here is there evidence, or we are saying the null hypothesis is that every bag of M&Ms will have 30% brown, 30%, 20% yellow, 20% red, 10% orange, 10% green, 10% blue. Okay, so our null hypothesis is that this distribution is true, this percentage distribution. The alternative is simply that this is not true. Okay, so you can also think of the null for this kind of test as being basically just that the stated probability distribution will actually hold. So the null hypothesis is that the probability of getting a brown M&M is 0.3. The probability of getting yellow and red M&Ms is 0.2. The probability of getting an orange, green, and blue M&Ms are all 0.1. So our null hypothesis, again, is just that these probabilities hold. And then the alternative, if you wanted to, you can just think of it as saying like at least one of these isn't true. So the null hypothesis can also just be thought of as those initially stated probabilities are true, and the alternative is simply that at least one of them isn't true. We only need one of them to be false for the null hypothesis to be rejected. If all of them are false, that's fine, but you only need one. So that's why it says at least one. On step 2, we state the significance level. Okay, so now on step 3, we're going to compute our test statistic. Now I'm just going to borrow this table here so you can see how this calculation is working. Okay, so you can see that I've typed out the calculation here, but again, I'm just going to show the little table so that you can kind of see where the numbers are coming from. Okay, so the test statistic is observed minus expected value squared divided by expected. So you can see that we have 6 different components contributing to this calculation because there are 6 different outcomes, the 6 colors. So the first value is 152 minus 152.7 squared divided by 152.7. So you can see that we are just working in pairs here. So I am connecting the observed and the expected count for brown first, and then I'm moving to yellow. So then I have 114 minus 108, 101.8 squared divided by 101.8. So that's the yellow outcome. Then I move to red. So I have 106 minus 101.8 squared divided by 101.8. And then I move to orange, green, and blue, and you can see it's the same pattern. So the observed 51 minus the expected 50.9 squared divided by the expected. And then the same thing for green and blue. So we're making that calculation C number of times, and then we're adding across all those fractions. So in this case, when I do the math out, I end up with 4.091028. So this is the test statistic for this chi-square test. Okay, so now we can take the critical value or the p-value approach on step 4, the same way we did before, but we're just using the chi-square table now and the chi-square curve rather than the student t or the standard normal. Okay, so the starting point for this is going to be the same. So the first thing I'm going to do is just sketch out my area of interest, so the critical or the rejection region. Now, here I'm drawing a right skewed curve because the chi-square distribution is right skewed and it starts at 0. So notice that the 0 is placed at the axes, and then I have my right skew curve coming out. Okay, we are testing at the 5% significance level, and we have 5 degrees of freedom here because there are 6 outcomes in the data set. So the degree of freedom for a chi-square goodness of fit is C minus 1, which is 6 minus 1, which is 5. Okay. So then I'll just mark down a point. This is going to be my critical value, which is on 5 and 0.05. Okay, and then my rejection region is always going to be in that skewed upper tail. So again, one of the things that's nice about the chi-square testing is that we don't have to move the rejection region around the curve depending on the alternative. It's always in the upper tail. So we have all 5% of our information in this upper tail. Okay, so we want to find the critical. So we go to our chi-square table. We identify our degrees of freedom, same process that we use for the t-table. And now we are just looking for the upper tail area that matches ours. So ours is 0.05 in this case. So as we look at page 1, you can see that 0.05 is not here. So we move to page 2. We have 5 degrees of freedom. And 0.05 is here. So we match that together and we get 11.070. So this is the critical value for this particular chi-square test. So if we go back here, we have 11.070. Our test statistic is therefore going to be over here somewhere, right? So we have x squared is 4.09. And then, of course, you can see that this is not in the rejection region, so we do not reject the null. So the way that we use this is the same as it was for the standard normal and the t-based tests. The way that we actually use these values does not change. It's just the table and our visualization of the region that changes. Okay, now if I take the p-value approach, it's going to be the same idea. So I start by sketching my chi-square curve. Then I'm going to mark down my test statistic. Okay, and then again, I'm always going to be working in the upper tail. So the p-value here is equal to the probability that a chi-square exceeds 4.09, which is going to be on 5 degrees of freedom. Okay, so to find this, just like with the t-table, I go back to my chi-square table. So I'm starting on page 1. I have 5 degrees of freedom. I'm looking for 4.09. So I scroll across my degree of freedom line, and I notice that, okay, 4.09 is bigger than the largest value listed on page 1. So then I move over to page 2. I'm still looking for 4.09 on the 5 degree of freedom line. And what I find is that it's smaller than the smallest value listed on page 2. So our test statistic is actually bounded between the last value on page 1 and the first value on page 2. And again, you read these tables horizontally, not vertically. So if you had them laid out beside each other, you would actually just see that 4.09 is between those two numbers. So just because 4.09 is between those two numbers, we can say that the area that we are interested in is between the two tail areas. So then we can go back and we can write then 0.9 is greater than this probability, which is greater than 0.1. So therefore, 0.9 is greater than the p-value, which is greater than 0.1. Okay. So it works just like a t-table. It's just that we're able to make more interesting bounds for the lower test statistics because we have the option of working with that first page. Now, how do we use the p-value? The same as before. We're just asking, is the p-value less than or equal to alpha? Because if it is, we can reject. In this case, the p-value is between 0.1 and 0.9. So anything between 0.1 and 0.9 has to be bigger than 0.05, which is our significance level. So therefore, the p-value is bigger than alpha, and therefore we do not reject the null. So then our concluding statement is at the 5% significance level, the data do not provide evidence that a standard bag of M&Ms does not follow the color distribution stated by M&Ms and Mars. That is, we found no evidence to suggest that the distribution that the company stated is not true. Okay, so we should expect that the distribution of the colors in a bag of M&Ms follows what the company stated based off of this test. Okay, so I'm going to stop the video here, and then as I said, I'll post a second video for the independence test, which is the second topic in this set.